So definitely we can make it with the NAND. Its truth table will be a little bit different, and also in that case we call it a S bar R bar latch. Why S bar R bar? Because you see, like, this terminal, if I set to 0 and other terminal set to 1, we set the output to 1. So setting this guy to 0, other to 1 is a set condition. So it's kind of an inverse of the set. That's why it's called a S bar, S prime as a label. So nothing to do with the logic function. This is just a label, just a name of the terminal, nothing else. This is to aid us to remember what the functionality is. S bar R bar, set condition is S bar is 0, R bar 1, and reset condition is S bar 1, R bar 0. Okay, and then hold condition is 1 1, and in this case in undefined condition is 0 0. Of course it will push that circuit both the terminal to 1 1, but as soon as you go to a hold, it becomes a rest condition for this gate. So this is an S bar R bar latch using NAND. All right, now going forward, now SR latch with control. Now notice that it's with the NAND, but we came back with that SR latch term, right? It is no longer an S bar R bar latch, because we can presumably presume that that this, whenever we set this S to 1 and R to 0, it's a set condition for us, and vice versa. S0 and R1 is a reset condition. Not only that, we introduced one extra signal called C. Okay, so C is a control signal, and truth table looks like this with this configured. So we have this back-to-back NAND gate here, and then which inputs are primary inputs are driven by another output of another pair of NAND gate, and then those NAND gates are driven by C, and one of them is driven by S, another is driven by R. Okay, so C is a common signal, but common is not the origin of the name C. I will explain it later. Okay, why it is called a C. You can right now think it is a control signal, and its functionality is just like this. If the C is held to 0, okay, that means no matter what the value of S and R, means it's don't care what's the value of S and R, if Qt was 0, Qt plus 1 is 0. If Qt is 1, Qt plus 1 is 1. Means internally what happens to this S bar R bar latch? This S bar R bar latch, for C equals 0, this primary input of this S bar, internal S bar R bar latch, becomes 1 and 1. And look at the truth table of the S bar R bar latch. 1 1 is my hold configuration. So it will hold whatever the value is being stored inside this storage. This is, if it is stored 0, it will hold it. If it is storing 1, it will hold it. So that becomes an hold condition for this new circuit. Okay, if C is 0, no matter what S and R value is, I hold the value. Now we make C equals 1. That means really the output of this, both of these NAND, which are driving the internal S bar R bar latch, depend on value of S and R, right? So the rest of the condition we make it, let's say C equals 1. Then we have couple of combination. S is 1, R is 0. So S1 means we have a 0 at this terminal of the NAND gate, which is driving the Q, and 1 at the NAND gate, which is driving the Q bar, that NAND which is driving the Q bar, right? So S with a 1, that becomes internal latch, become S bar becomes 0, and R equals 0, internal R bar become 1, which is a set condition for internal S bar R bar latch, that means for the whole circuit it becomes a set. So no matter what the QT value is, C equals 1, S equals 0, S equals 1, R equals 0 will give you an QT plus 1 as 1. Similarly, similar logic, 1 with C equals 1, S equals 0, R equals 1, no matter what the QT value is, it will reset the whole thing. It will set the output Q at the T plus 1 iteration as 0, right? So that becomes my reset condition. And correct is saying, you see that we have labeled the S and R correctly, because S is 1, R is 0, that's my set condition, and S is 0, R is 1, that's my reset condition. Of course, we are assuming at that point C is set to 1. Then let's consider the other configurations of S and R with C equals 1. We can have 0, both 0, 0. That becomes a hold condition. If the QT was 0, it will be held to 0. If QT was 1, it will be held to 1. And 1, 1, 1, C equals 1, S equals 1, R equals 1, no matter what QT is, QT T plus 1 become 1 and Q bar T plus 1 become 1. This is kind of becoming a rest condition now, right? So 1, 1, 1 is a rest condition. Now, why we bothered to complicate my circuit? We have already 2 AND gate back-to-back latch. It was perfectly doing its job of storing a bit. Now we added some extra circuitry, have a bigger truth table and all this stuff, little bit complex. Why we did so? If you notice now, in the bigger truth table, you have 2 hold condition, isn't it? When C equal to 0, no matter what the S and R is, or if C equals 1 and S and R both are 0. Those are 2 hold conditions, this white part of the table, truth table. Now, we have 2 hold condition, and let's say we don't want the second hold condition where C equal to 1 and S and R are 0. Let's say we don't want to use it, okay? Then we have one set condition, that is the green row, one reset condition, red row, and another white topmost 2 rows are for the hold. So we already have the function set, reset, hold, right? So we don't need really the bottom half of the truth table, that is this bottom white and this gray part of the rest condition. We don't need them, right? If we think so, then look at the set and reset condition configuration. C is 1, that's fine. Now S and R within this green and red row, they have exactly inverse relation, isn't it? Your set condition is 1, 0 on the S and R, and reset condition is 0, 1 on S and R, while C is 1, okay? So they have the inverse condition. So with that observation, what we can immediately do is this. Instead of having S and R 2 terminal, we combine them into one terminal called D and make this internal latch, internal NAND gates of that previous latch, SR latch with control, just made it an inversion relation with the D. Okay, so D, for one of the input it goes straight, and other of the input of the NAND it goes inversely. So internally it becomes an SR latch with control, but externally as a primary input of this logic component is not SR anymore, we call it a D. Now what happens? See, like controls is 0, C is 0, no matter what X is, it will hold the previous value, right? QT is 0, QT plus 1 is 0. QT is 1, QT plus 1 is 1. And if control is 1, then I have If D is 1, I'll store 1. If D is 0, I store 0. And we just eliminate our race condition. This circuit cannot have a race condition because we are forcing the two inputs of the internal SR latch with control as an opposite logic relation. Always it cannot be like 1 1 or 0 0. It will always be either 0 1 or 1 0. Okay, and with the C, the control signal, we have the hold configuration. So we have now both hold configuration, set configuration, reset configuration, and we eliminate the race condition from this component. Advantage of doing this is whoever is using this storage element, like some other circuit, right? Digital circuit is basically driving this storage element. That circuit does not need to consider an race condition. Thus, the circuit building would be much easier. Circuit designing would be much easier whoever is using this component. So for the circuit who is using this NAND SR latch, they are usually a little bit complex because it need to make sure it does not produce a race condition for SR latch. For D-latch, there is no race condition. So your whoever circuit, the top level system is using this storage with a D-latch, it is simple, more simple than using some system using SR latch. So that's one thing.